And the key idea that we reviewed was the idea of Lorentz transformation. Such that if we had space-time coordinates, which we denote by a 4-vector, where the time coordinate and then the 3 spatial coordinates form a 4-vector, then we have, if we do a Lorentz boost, that is to say, go to a co-moving reference frame, that was co-moving, say, along some chosen axis. Then we had that the new space-time coordinates are related to the ones in the old reference frame by a linear transformation where this Lorentz boost matrix has the form with zeros elsewhere. Where gamma is 1 over the square root of 1 minus beta squared, and beta is b over c.
Sorry, I don't quite understand. Why are we being a prime?
I mean the x prime of mu. Either way, I'm just saying these are the variables in the new reference frame. Okay. So that is the foundation, and then we describe any object, a general 4-vector, was any set of 4 coordinates whose transformation under a boost or a general Lorentz transformation, which could include a rotation, transforms according to the same Lorentz transformation. And examples that we saw of this were the 4 velocity, whose spatial coordinate is proportional to the speed of light times the relativistic gamma associated with the local velocity u. For momentum, P is equal to the relativistic mass, the rest mass times the 4 velocity, and we saw that this was equal to a 4-vector whose spatial component is the relativistic momentum, which is the relativistic mass times the kinematic speed, and the time component was the energy, which is the relativistic mass over c squared over c. And the other thing we discussed at the end was the notion of kinematics and the Minkowski force. Nu, which is the derivative of the 4 momentum with respect to the proper time, which is a scalar. And we showed that the time component of this was the relativistic gamma associated with the speed times the factor that has to do with the rate at which work is being done in that frame, and gamma, where F is the kinematic force, is the relativistic change in momentum with respect to the local time. All right? Now, where we were last lecture was thinking a little bit about how force looks in different reference frames. Because of the fact that the force is defined in terms of the derivative with respect to time in our frame, and time looks different in different reference frames, the transformation is messy in the same way that we saw velocity transformations. The transformations on the local velocity is messy. We saw, for example, if we make a transformation, if we do a boost, then u prime parallel, let's say the x component, we saw that this is what we have from Galilean transformation, right? You just, if you move along the x direction, you catch up by the amount that you're moving, but in fact we have to normalize this by this factor having to do with time dilation, right? And a similar kind of messiness happens here. So what we're looking at was the following particular example, where we said, let's imagine we have some spatial trajectory. I mean, I'm not talking about space-time here. This is just the trajectory, just looking at this plane. Let's say I have some particle moving along. Here's its local velocity with respect to the reference frame S. Okay? And suppose, from my perspective, here in the lab, sitting here with you, standing here with you, there is a force, which is the local rate of change of the momentum with respect to the local time in the lab frame. So this is all in the lab frame. Okay? And so now I can write down what there is some 4 vector here. Well, here it is. Okay? Now, in the rest frame of the particle, well, this thing is at rest in its frame. So its local velocity is 0 in its frame. So this time component is 0. And gamma is 1. And this is whatever the force is in the local rest frame. So the prime frame is the local rest frame of the particle. Okay? So now what I want to do is relate what the force in the rest frame, the instantaneous rest frame of the particle is, how that is related to the force seen by me or you in the lab frame. Okay? So the way we do that is we break this up into a component which is parallel. So there's a vector which is parallel to the speed, or the velocity, I should say, and a component which is perpendicular. Okay? Because the Lorentz transformation is different for those different components, right? So what we see here is that, so F parallel is equal to gamma of u, which that's the boost. We're boosting now into this frame. excuse me, this is absolutely wrong. It's the K. So this is K0, and this is K. That is, we're looking at, it's the Minkowski the 4 vector, which we have to transform, not the kinematic vector. So K parallel plus U K0. That's a Lorentz transformation. That relates the lab frame and the instantaneous rest frame. K0 plus U K parallel. All right. Now, let's look particularly at the space component of this 4 vector. This is equal to gamma of so this is the lab frame, this is the instantaneous rest frame. In the lab frame, the particle is moving with velocity u, so its space component, we said, is gamma f equals gamma u times k parallel prime. But k parallel prime, it's in its instantaneous rest frame, so that's equal to that. You have that written over here. And the 0 component is 0. So what that tells us is that the component parallel to the boost, which is the direction of the instantaneous velocity of the particle, the parallel component of force is the same. The perpendicular component of the 4 vector does not change under Lorentz transformation. That's what this says. So only the component that's parallel to the boost that changes. In the instantaneous rest frame, this is F prime perp. But in the lab frame, it's moving with speed u, and so this is its speed. So what we see here is that the perpendicular component in the lab is related to the perpendicular component in the rest frame of the particle through the relativistic bound. Okay? It's messy, but that's just the way it is. Now, why did I go through this business? Well, what we want to understand is relativistic, yeah.
Isn't prime the rest frame?
Yes, sorry, I have it backwards. Thank you. That is correct. All right. So now what we want to understand is electrodynamics. And in particular, we want to understand the way in which electrodynamics is consistent with relativity. Now, we already kind of have a hint of the fact that electrodynamics has something to do with relativity by thinking about magnetism. So I claim that we should have had a clue about this from the beginning. So magnetism the relativistic phenomenon. What do I mean by that? Well, let's consider the following thought problem. Let's just look at the Lorentz force of a charge or on a charge moving in a magnetic field. In particular, let's look at the following scenario. Let's suppose I have a wire, and in that wire there is current. Okay? And let's suppose this is a neutral wire. So it has no net electric charge. And here I have a point charge, Q, which is moving with some velocity U. What is the force seen in the lab frame? Here's the lab frame, this charge is moving on. What is the force acting on this moving charge? What direction is the force in? Is there a force on the charge? Yes. And in what direction is that force? It's towards the wire. How do we get that? So let's put on some coordinates. Let's call this the x direction and this the y direction. There is, of course, a magnetic field, which is in, if this is x, this is y, z is out of the board. There is a magnetic field into the board in the minus e direction, right? And then u cross b is up. So there is a magnetic field which is falling off like 1 over the distance from the wire, and there is a force in the y direction, right? So the force in the lab frame, we know, is equal to the Lorentz force, okay? But what happens if I jump onto this charge into its local reference frame? Well, it's still got to move towards the wire, right? Because the physics is the same. It still moves, it's still attracted to the wire. But this force is 0, right? Because the local speed in the local reference frame of the charge is 0. So as I'm moving along with the charge, if I'm being attracted to the wire, it can't be due to a magnetic field, because the magnetic field that is exerted on the charge depends on the speed of the charge in that particular reference frame. So why in the world would it move towards the wire?
Electric field.
There's got to be an electric field in that reference frame. Even though there's no electric field seen in this reference frame, in this reference frame, E is 0, right? Because it's neutral. There's only a magnetic field. But in the co-moving frame, moving with the charge, there has to be an electric field, which exerts a force that attracts this charge to the wire. So the lesson learned here is that one person's magnetic phenomenon is another person's electric phenomenon. Okay? I can't say one man's. Two persons. I could say it, but I wouldn't say it. Right. So what we want to show now, yes, please.
In the lab frame, the frame, think we call it that.
The lap frame is here. The thing is moving.
Where we see
the
it.
instantaneous rest frame of the charge
So,
is.
aren't there still charges in the wire even in that frame? Exerting, or, having a magnetic field?
There will be-
I'm sorry, electric field, but they're just moving?
Yes, okay, so let's make a model of this. And this is a beautiful model that was first discussed by Purcell. So I'm going to talk about the Purcell model. Does everyone know the book by Purcell? It's one of the Berkeley series on electromagnetism. It's supposed to be a sophomore level book. It's not really. If you've never read that book, you should. It's an awesome book. Really, Griffiths is, it's take Purcell and make it Paging Leavenworth. And Griffiths takes Purcell's model and discusses it as well. So if you have it, you'll be right. So here's the idea. The idea is let's treat the problem where I have two line charges. Okay? So I'm going to have some line of positive charges and an equal density of negative charges. Okay? Such that although I drew them as separated, let's imagine I treat them as perfectly smooth and on top of one another so that the net charge is 0. So in this reference frame, there's no electric field. So in the lap frame, the electric field is 0. Yes?
If the charge is getting closer to the wire, the B field is changing, so doesn't a changing B field also cause the electric field?
You mean that in the frame of the charge, as it's moving, it sees a changing magnetic field, and that causes a changing magnetic field. Indeed, I mean, so one has to look at the physics in one reference frame or another. So if we're looking at it from the point of view of the lab frame, the phenomenon is purely electric. That's right, purely magnetic, right? Because in our reference frame, B is constant in time. In the reference frame of the charge, well, it sees something different. The dynamics must be the same because the physics must be the same. But we would need to think about the fact that we're not at every point in time in the same reference frame. We would have to, at each point in time, jump into, if we want to treat this problem from the point of view of special relativity, then at each instant of time we have to change reference frame because the instantaneous velocity is changing. So the way to think about this problem and what we want to do is looking at it at one instance of time. Right now, what is the force? Okay? To think about the full dynamics and differential equation, we need to do more. All right, so now what is the magnetic field? Well, to do that, what we're going to assume here is that each of these charges is moving with a speed v in equal and opposite directions. Okay, so there's a line of positive charges moving to the right and a line of negative charges moving to the left. And there is a charge density per unit length. So there's a linear charge density minus lambda and plus lambda, such that the sum of them is 0. So in this, the net charge, linear charge density is 0. But there is a current. What is the current associated with this collection of moving charges? Well, each line charge makes a current I. Since this charge density is moving in the minus direction, its it contributes the same amount of current as the positive charge density. If they were moving together, there would be no current, but they're moving in opposite directions, right? So the net current is equal to plus minus lambda times minus V, which is 2 lambda. That's the net current. So I ask you now, what is the magnetic field associated with this current?
That divided by R divided by C something.
Yeah, it's one of our ones. See, how would I do it? How would I find it if I don't remember what it is? Ampere's law. So this is the question, do we need to go faster at the beginning of this course or not? Really, the question is, how much do we have this at our fingertips? And we'll remember that Ampere's law tells us that, you know, I dl is equal to the, I'm sorry, d dot dl is equal to the enclosed current, which is I, and in this case you get this 4 pi over c, so this is 2 pi r, and b, so b as a function of r, which is in the z direction, is equal to 2 times the net current over r. Okay? All right, so there is a force in the lab, this is on the lab frame, which is in the y direction, which is equal to q, u, which is in the x direction, over c, times b, which is 4 lambda v, using this expression, divided by c r. Okay? All right, so now let's go to the co-moving frame, moving, or this is the instantaneous rest frame of Q. All right, so in the frame now, here's the wire, here's the charge. Charge is a scalar, that's an empirical fact. Charge, what we call charge, is the same in all reference frames. What will we see in terms of these charges? Well, of course, we're going to start catching up to these charges, and those charges are going to be going away with us, from us faster. I mean, they're not moving at the speed of light, so we can catch up to them. And the other ones will move away faster. So we'll have some v minus prime in this frame, which is the instantaneous rest frame. And some of the positive charges will be moving with some different speed as well. And what is that speed? V plus or minus? Well, it's the thing we just wrote up there, right? So we're moving with, we were moving with speed u. Now we boost up speed u. So what we see is v either minus or plus u. That would be the Galilean transformation. And then we normalize that by the minus or plus u v over c squared. Okay? So these charges are moving at different speeds. However, there's one other very important fact. We know that the distance between things appears differently in different reference frames. Which means that there is going to be length contraction for the distance between those charges, and the amount of length contraction will be different for the positive charges versus the negative charges, because they're moving at different speeds. Which means that the negative charges are going to be very much more bunched up, whereas the positive charges now are less bunched up compared to what they were in their own reference frame, because the negative charges are moving faster than the positive charges. And things contract by an amount proportional to gamma, which depends on how fast they're going. So there is a lambda minus in the prime frame and a lambda plus in the prime frame. Which means the net charge density in the prime frame, the co-moving frame, where this is at rest, which is lambda plus, well, I'll call this is going to be negative, right? Because there's a more negative charge density than positive charge density, which means that this, assuming Q is positive, it will feel an electric field which attracts it to the wire. That is to say, we will have a Y component of the electric field, which will be equal to from Gauss's law, and this will be in the, this will give us the force, the Y component of the force in the prime direction will be Q in Y prime. There is no magnetic force on this particle at this instance of time because it's not moving, right? There's only an electric force. And our goal now is to show that this force is the force that we expect to see by just doing a Lorentz transformation on this force. What force do we expect to see? Well, that's what we just calculated. We said that the force, the perpendicular component of the force, perpendicular to the boost direction, in the instantaneous rest frame of the particle should be whatever the gamma factor is associated with that speed times the perpendicular component in the lab frame. Okay? So this should be equal to gamma of u times that force, which is equal to q u over c for lambda v over c r. Which means that we should find that the electric field in this reference frame is equal to gamma u for lambda u v over c squared r. Or said another way, that this is gamma u over times the z component of the magnetic field in the lab. So what we want to show now is that there is an electric field seen in the local rest frame of the particle that is exactly related to the magnetic field in the lab frame by this transformation. And we can understand why that must be true, because it must be the case that the sources seen by the charge in its own rest frame are different because of length contraction. So magnetic phenomena are intrinsically weak compared to electric phenomena. The only reason we see them at all is because electric forces are so strong that the tiniest, most tiniest imbalance of charges gives rise to a force that we would notice. Even though if this is not moving near the speed of light and V over C or U over C is not very big, it could be tiny, the multiplication of that tiny effect by this huge net charge, whatever this net charge is enough to give me a substantial force that I will notice. The only reason we see magnetic phenomena is that electric forces are so big. So let's do it. Let's see if it works. What is the net charge? Well, the net charge here, what we need to do is calculate what the charge density is seen in this reference frame. Well, that's going to be plus or minus gamma V plus or minus times whatever the charge density is in its own rest frame. We know that the distance between charges shrinks. Therefore, the charge density increases. It increases by the factor gamma. And that factor depends upon what the speed is compared to when it's at rest. Okay? However, you notice the charge density that we see in the lab frame is not the charge density it's not the same lambda 0. Because these charges are moving. Yes, Boyer?
Question. It seems that this construction depends on the choice of directions for B plus and B minus.
It does. I mean, this is a particular configuration which says if we have charges moving like this, okay, then this will be the magnetic field. And then what is the electric field? I mean, if we had a different choice of directions, we have different fields, different forces, and we would analyze that independently. This is for a particular choice. Okay, so the other thing to note here is that lambda, so seen in the lab frame, so let's see, I better be careful. This is seen, I should keep my notation a little bit more clear. V plus or minus is what I'm calling with the prime, is the velocity of the charges seen in the prime frame. Okay? V is the velocity of the charges seen in the lab frame. So the lambda seen in the lab frame is equal to the length contraction of the lambda in its own rest frame. In the lab frame, the charges are moving. So the charge density we see in the lab frame is different from the charge density in its own reference frame. Of course, they're contracted by the same amount because they're moving at the same speed, only equal opposite directions. So putting that all together, what we see is that the lambda prime plus or minus is going to equal lambda, a gamma of v. Let's see, I have to, where is it? Plus or minus gamma of v plus or minus times lambda 0, which is lambda over gamma something. Plugging in here. All right. So now we have to figure out what all these things are. What is gamma of v plus or minus? Well, that's equal to 1 over the square root of v plus or minus squared over c squared. We got to plug that in. We then plug it in gamma of v. This is in all in prime frame. And it's a bunch of tedious algebra. And what you find is the following. That this is equal to, so that v plus or minus 1 minus or plus uv over c squared divided by the square root of 1 minus u squared. Looks good. All right. So what we find from this then is that the net charge density is as expected. It's a negative charge density, where lambda is the charge density in the lab frame times gamma u, because of this factor that ends up here. Okay? Yes?
Isn't the, so just I'm remembering from undergraduate,
Uh-huh.
the, like a charge in a moving frame, doesn't the field changes, doesn't it?
Well, that's what we're, in fact, we're disproving, which is to say that the electric field in the moving frame is different from the electric field in the lab frame. So what we say, what we're out to prove here is that the electric field seen by the charge is related to the magnetic field seen in the lab. Let's complete it, and then we'll try to reemphasize the main points. So we've shown by thinking about length contraction that as seen in the rest frame of the charge, the wire has got a negative net charge to it. And so there is an electric field in the y direction, which is given by twice, just according to Gauss's law. That's what one would find, which is equal to minus 4 lambda u v over r over c on each of these guys times gamma of u. No, that's minus. Just the way I define it is whatever the net charge is from Gauss's law, the electric field comes out. So it's the negative y direction out there. All right, so the claim is that this should be equal to this. Does it? Let's take a look. What we found was the magnetic field in the lab frame, the magnetic field had a z component, which was equal to the net current over c times r, which was equal to 4 lambda v rc. So this is equal to u over c gamma u over c vy. Yes. All right. So the key points that we learned from this is the following. One, E and D transform into one another. In different reference frames. I mean, that had to be true even in Galilean relativity, in some sense. Moreover, what we see here is that we can understand that in that the sources rho and j look different in different reference frames. So what we can say here is that it doesn't really make sense to talk solely about electric fields or magnetic fields. We should talk about electromagnetic fields. Because one person's magnetic phenomenon is another person's electric phenomenon. They will be described differently in different reference frames, but they are the same physics. So in this problem, the moving charge at this very instant of time, if there's a current in the lab frame, it feels an instantaneous force which will start to pull it towards the wire. And we would attribute that to a magnetic field arising from moving charges. Whereas at that same instance of time, as seen in the rest frame of the charge, it sees a net negative charge, which makes an electric field like this, which pulls it towards that. So this is in the lab frame, written as a B, and in the charge frame, there's an E. Yes?
So, in the whole analysis of the charge frame, what happened to the magnetic field that would arise from all of those negative charges?
It's there. But why isn't there a force on the charge due to that? It's a good question. There indeed is a magnetic field due to these, because these charges are still moving. So there is an on net. What happened to the magnetic force on that charge?
It's not moving.
It's not moving. So the only force on it is electric in that frame. Good question. All right. So what we would like to do and where we're headed in the grand finale of the course on Wednesday is to try to understand what the transformation law is for electric and magnetic fields. Why can't we just write down some 4 vectors and write down a Lorentz transformation for E and B? What would be the time component for each of them? Because we need 4 components. It's certainly not clear. We don't know what the 4 vector is. for which these would be the spatial components. In fact, the E and B vectors, standard Cartesian vectors, are not the spatial components of individual 4 vectors. There's no E mu or B mu. In fact, instead, what there is a 4 tensor for which E and B are components, the famous F mu nu. Which is another reason CGS units are the right things. Why in the world would the components of this have different units? They have to have the same units. That's why half of Jackson's written in SI and half of it's written in CGS, which is ridiculous. Why would you do that? All right. So, to get there, we want to think a little bit more carefully now about the way in which we did this problem was we calculated how the charges and currents change by looking at the length contraction and putting that into, it's a very tedious way. It's correct, but it's very tedious. We can get this in a much more elegant and quick way by noting that the sources themselves make up the components of a 4 vector. So the claim is that if I put the charge density together with the current density, that this is a Lorentz 4 vector. If that's true, then we know how to transform charge and current in different reference frames by just doing Lorentz transformation. Now, we certainly know that charge and current are related Galilean, right? If I have a charge density and I start moving, then it's a current, right? So there's no surprise there that one person's current is another person's charge, depending on the moving. The only thing that is additional is that we have length contraction, which means that the charge density can change, not just the current density. In the same way that we know time can change when we go relativistically because of time dilation. Okay? So how are we going to look at this? Well, what we claim is that charge is conserved. That's in all reference frames. And that is expressible mathematically through the continuity equation. All right? So, now we want to say that this is true in a different reference frame, but we have to transform in that new reference frame not only the spatial coordinates, but the time coordinates according to the Lorentz transformation. So, now we know how space and time change, so we can use the chain rule. First of all, let's break this up into components, one particular spatial component which will be parallel to the boost. So we'll call x parallel the direction of a boost. That could be, say, the x direction, or it could be the y or z, it doesn't matter. So now let's write this out. In terms, just expanding the divergence in terms of the derivative with respect to the particular coordinate we're calling the parallel component and the others. Okay? Now, we have x parallel is equal to gamma x parallel minus v, or x parallel in the prime frame, excuse me, if we boost by amount v, and t parallel t in the prime frame is gamma t minus v over c squared x parallel. That's other explanation, and x prime, the perpendicular component, is unchanged. So now we can use the chain rule to see how the derivatives go. So d by dx parallel is d by dx parallel prime dx parallel prime dx parallel plus dt prime dt prime dx parallel. And that's then gamma right. Yeah. Yeah, okay, good. And similarly, dt is gamma dt prime minus v by dx. Okay, so putting that all together, plugging in these derivatives into that expression and collecting terms, we find the following thing is true. D by dx prime parallel times gamma j parallel minus v rho plus that plus d by dt prime gamma rho minus v over c squared j parallel is equal to the right-hand side. Okay. If charge conservation is true in all reference frames. And so from this, we see that j parallel prime is equal to gamma j parallel minus v over c rho. And c rho prime is equal to gamma c rho minus v over c j parallel. And j perp is unchanged. And so, because of the way space and time transform, the components of charge density and current density must transform as a four vector in order to maintain charge conservation in all reference frames. Okay? And we see this length contraction factor if we go to a reference frame, if in an initial reference frame where the charge density were 0, in a new reference frame, the charge density won't be 0 because of this gamma v over c j parallel. And that's what we just saw. We had a situation where the charge density was 0 in one reference frame, in another reference frame, it wasn't. Okay, so these are the sources. From this, we can begin to get some expressions for how the fields transform into one another. So for this, we're going to look at another kind of configuration where we're going to look at the following. Let's imagine that I have two very long, very extended parallel plates. Okay, so this is like a parallel plate capacitor, which has a charge density plus or minus sigma on it, which would make an electric field that's uniform, ignoring the fringing fields between them, right? Let's call this direction the x direction, this the z direction, this the y direction. So the x direction is the direction of the field. Let's also assume that although I have to have some source and drain on each side, there's some current flowing which is equal to, right, so there's some surface current density in the z direction and opposite amount on the other side. So what this means, there's an electric field that's uniform between these plates. There's also a magnetic field uniform between these plates, which is in the y direction. All right, does everyone understand the configuration? We have flowing surface charge on this plate, which is flowing at constant speed, gives a surface current density K. It's also charged, it's some surface charge sigma. It has uniform E and B in between this. This is the lab frame. Now what we want to know is what is the electric field and magnetic field seen in moving frames. Okay. So in the lab frame that we have, so this is the lab frame. In the lab frame, the electric field is in the y direction. No, it's in the x direction. The electric field is in the x direction as I've drawn it, and it has the size 4 pi sigma everywhere between those plates. The magnetic field is in the y direction, and it has the strength 4 pi times k over sigma. So now, let's do the Lorentz boost. So boost along the z direction. Okay, so we're going to now be boosting in the z direction, moving in the same direction as this current. So we have in the boosted frame, we have new current, which is less, of course, by an amount depending on the speed in which we move. We boost in the v direction with speed v. And then we have the gamma factor out front. That's according to what we just wrote down about the j's and the rho's, how they transform. And the sigma in the prime frame is gamma sigma minus v over c squared az. That's Lorentz transformation. So in this reference frame, what do we see? Well, we have again an x component which depends on the new charge density, just like before. But the new charge density is related to the old one, so this is gamma 4 pi sigma minus v over c squared 4 pi kz, which is equal to gamma ex minus v over c vz. Right? So the electric field seen in this frame is related to the electric and magnetic fields seen in the lab frame. Similarly, By, write it over here. I want to delete this. The magnetic field in this new is equal to 4 pi over c, the new current, surface current, and the new surface current is related to the old surface current. So this is gamma 4 pi over c kz minus 4 pi sigma over c times v. So that means that in this frame, we have Bz minus V over C dx. Finally, what happens if we boost along this y direction? Boost along y. Well, this is now unchanged because we're boosting perpendicular to the current. The sigma changes, becomes gamma sigma. Again, we're boosting parallel, so that is the only factor. But now we also have a new ky minus gamma times v sigma. This is a new. So what we see now is bz prime is equal to bz. Dx prime is gamma dx, but now we have a new component, by prime is equal to minus gamma v over c dx. So we can summarize these in the following way. And this will be our conclusion for today. We'll pick this up next week. The general transformation law can be expressed as the following way. Given E and B in frame S, boost to frame S prime, the electric field and magnetic field transform as follows. So, what this says is that the components of the field which are perpendicular to the boost direction transform into one another. The components that are parallel to the boost direction don't transform. And that's what we saw in this case. When we boosted along Z, the Z component of the magnetic field didn't change. But the components that are perpendicular, when we boosted along, in this case, Y, Well, the z component and the x component transformed into one another. Now, these expressions look pretty messy. They look nothing like the Lorentz transformation that we wrote down for, any of our four vectors, because E and B are not the components. They're not the spatial parts of components of four vectors. They are actually the components of a four tensor. And it's that which we head for next week, and the more general, so-called manifestly covariant formulation of electrodynamics. Okay, we'll leave it there for now. I would very much like you to fill out these forms.